Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today we are going to discuss about the module Symmetries in Quantum Mechanics under the paper Quantum Mechanics 1. So students, let us see what all we are going to learn in this module. Firstly, we'll get the general viewpoint about symmetries, what are the different types of symmetries and how we can understand them. Then we'll discuss about the spatial translations and the conservation of linear momentum. From there, we'll move on to discussing the translational invariance of the Hamiltonian. From there, we will also try to generalize these results for many particle systems. And finally, we'll study the displacement in time, and we'll see that the displacement in time leads to the conservation of energy. So in this module, we turn over to the topic of symmetries in quantum mechanics. After presenting a general overview of symmetries that exist in the physical laws or in the phenomena occurring in nature, we shall find that a symmetry operation on a given physical system has associated with it the law of conservation of a dynamical observable. In other words, if the Hamiltonian of a physical system is invariant under a certain symmetry operation, it would then imply the constancy of a physical observable. So, in this module, we shall specifically study the continuous geometrical symmetries such as translation, that is displacement in space, and time of a physical system. We shall find that the conservation of the linear momentum of a physical system is a consequence of the translational invariance of its Hamiltonian. Similarly, the total energy of the system is also conserved if the system is invariant under translations in time. Space translation. Here we will discuss the notion of symmetry. First of all, what do we mean by symmetry? Generally, any given object is said to display symmetry if it is found to be invariant under a certain operation or a transformation. In this module, we will examine the different types of symmetries that exist in the physical laws or the phenomena that occur in nature. So, for example, if we take the Newton's laws of motion, then the equation, that is force is equal to mass times the acceleration, that is the double derivative of the position vector with respect to time, is symmetrical under the translation in space. So what this means is that if we do a transformation in the position vector where the vector r is transformed to the vector r prime such that the vector r prime is given by vector r plus vector a, then the corresponding acceleration given by the double derivative of vector r prime with respect to time turns out to be equal to double derivative with respect to time of the vector r plus vector a, and this turns out to be equal to the double derivative with respect to time of the vector r, since a remains constant in time, that is the displacement a is constant in time, and thus we can see that even if we make a transformation of the position vector going from vector r to vector r prime, the force F does not change under such a translation or transformation, and hence we can say that the force is invariant under space transformation or space translation. Newton's law under rotations. Now, taking this discussion of symmetries further, let us also see another type of translation, that is translation in time. And let us see what kind of results we get when we do such a translation in time. So, supposing if the time t undergoes a translation to t prime such that t prime is equal to t plus alpha, where alpha is a constant displacement in time, then also we see by a similar exercise that we did earlier that the Newton's laws of motion remain unchanged. That is, the displacement in time has no effect on the physical law. So in this manner, we can also say that the Newton's laws under translation in time are invariant. That is, they remain invariant whenever we make such a transformation in time. Here, it is important to note that the Newton's laws are represented by the vector equation force is equal to mass times the acceleration. So, therefore, if one was to rotate a vector or equivalently rotate the coordinate system about a given axis, the vector and accordingly the acceleration vector A would also undergo a transformation. That is, vector A would change to vector A prime. We can consider an example where we rotate the coordinate system about the z-axis by an angle theta, such that the force goes from vector F to vector F prime under this kind of a rotation, and the x component of the force changes accordingly as F prime x is equal to Fx cos theta plus Fy sin theta, where Fx is the x component of the original force and Fy is the y component of the original force. So, when the force undergoes this kind of a transformation because of rotation about the z-axis through an angle theta, we also see that correspondingly the acceleration vector also goes a similar transformation about the x, and we can see that for the x component of the acceleration vector we can write a similar equation as we have written for the force vector, that is a prime x is equal to ax cos theta plus ay times sin theta, where ax is the x component of the acceleration prior to the rotation and ay is the y component of the acceleration prior to the rotation. And we can see that the laws of motion of Newton also remains invariant under rotation. These simple symmetry operations of geometrical translations and rotations manifest that ordinary space is homogeneous as well as isotropic. What we mean is that under such space transformations or translations of geometrical translation and rotations, one can see that the space is homogeneous or that the properties of the space remain the same when we move from one point to another, either through a geometrical translation or through a rotation. And similarly, when we say that the space is isotropic, what we mean is that the properties of space remain the same in all directions from a given position. That position could be a position in time or it could be a position in the normal geometrical space. Further, in quantum mechanics, there is an intimate relationship between the law of conservation of a dynamical observable and the corresponding symmetry operation of the physical system. What this means is that whenever we have a symmetry operation in a physical system, we can always see that this supports some kind of a law of conservation of a dynamical observable. We can see this through an example also. Supposing if we have or if we take the Hamiltonian of a physical system and we say that the Hamiltonian is invariant under a certain symmetry operation, then what it would mean is that it would correspond to the constancy of a physical observable. The symmetries may be broadly categorized in two groups. One, the geometrical symmetries associated with space and time, and two, the dynamical symmetries which are associated with the particular features of the interaction involved. A typical example of a dynamical symmetry is the one observed in hydrogen atom, where the energy level of the atom exhibits n square fold degeneracy, where n is the principal quantum number of the atom, which is a consequence of a special symmetry of the Coulomb interaction. The continuous symmetries associated with displacement in space and time and rotation in space are to be distinguished from the discrete symmetries which are defined by the operations of inversion of space and time. While the continuous symmetries are known to be valid universally, independent of the nature of interactions involved, the same does not hold in the case of discrete symmetries. In the next module, we shall discuss these in some detail. There is yet another type of symmetry, that is the permutation symmetry, which has a central role in quantum mechanics. It turns out that the systems containing n identical particles are either totally symmetrical under the interchange of any pair of particles, in which case the particles are known to satisfy the Bose-Einstein statistics, hence are called bosons, or totally antisymmetrical, in which case they are said to satisfy the Fermi-Dirac statistics, and the particles thereon are called fermions. You must have learnt in your undergraduate course that half-integer spin particles are fermions, whereas the zero or integer spin particles are bosons, and may have also studied the basic elements of Bose-Einstein and Fermi-Dirac statistics. Translational invariance and conservation of linear momentum. As we were discussing earlier, that whenever there is an invariance associated with a symmetry operation, then we can always associate the conservation of some kind of a physical observable. And one such case is that we can show that if we have translational invariance, then we get the law of conservation of linear momentum. So in order to analyze the connection between translational invariance in space and the conservation of linear momentum, we can start by considering a system that consists of a single particle described at a given time by the spatial wave function psi as a function of position vector r. The translation of a point particle located at the position vector r with momentum vector p is defined by the following two equations. The position vector r goes to position vector r prime, where position vector r prime is given as being equal to position vector r plus position vector a. Similarly, the translation of the momentum vector from momentum vector p to momentum vector p prime is given as momentum vector p prime is equal to momentum vector p. That means that the momentum vector remains unchanged under this translation. Thus, the translated wave function of the particle is to have its new position vector r prime, and this turns out to be the same as the original wave function at position vector r. That means the wave function psi prime as a function of position vector r prime is equal to the wave function psi prime as a function of position vector r plus position vector a, and this turns out to be equal to the wave function psi at position vector r, or as a function of position vector r. Translation in space and the momentum operator. Now, based on the analysis or the treatment that we've done earlier, we can say that the displacement, as we defined earlier, is equivalent to the one in which the origin of the coordinate system is displaced by a vector minus a. So, what we are wanting to say is that if the position vector r is translated to the position vector r prime, where the position vector r prime is given as position vector r plus position vector a, this same situation or the same condition can be replicated if we move or translate the origin of the coordinate system by the position vector minus a. In that case, the wave function for such a translation is given by psi prime r prime is equal to wave function psi as a function of position vector r minus position vector a. And this action of transforming the wave function psi as a function of position vector r into wave function psi prime as a function of position vector r prime is expressed by expanding the above equation in Taylor's series. So we have the wave function psi prime as a function of position vector r as given by wave function psi as a function of position vector r minus vector a dot vector del times wave function psi as a function of position vector r plus 1 upon 2 factorial times within brackets minus vector a dot del vector whole square times wave function psi as a function of position vector r minus and so on. And this series expansion for the wave function psi prime as a function of position vector r can then be rewritten as summation over n going from 0 to infinity within brackets minus vector a dot vector del whole to the power n upon n factorial whole times wave function psi as a function of position vector r. And this can then further be simplified as exponential to the power minus vector a dot del vector whole times the wave function psi as a function of position vector r. Here dot basically represents the dot product between the vector a and the del vector. Now the operator del vector, that is the del operator, is expressed through the momentum operator p, given by operator p is equal to minus I h cross del operator, and we get wave function psi prime as a function of position vector r is equal to exponential to the power minus iota by h cross times vector a dot momentum operator whole times the wave function psi as a function of position vector r. So basically what we have done is that in this result we have substituted the value for the position for the momentum operator in the above equation that we have derived for the wave function psi prime, and we get this final relation. Unitary operator of translations. Based on the result that we have obtained earlier for the wave function psi prime, we can see that the momentum operator is directly connected with translations in space. Thus, if we have an infinitesimal translation, the exponential term is expanded to get wave function psi prime as a function of position vector r is equal to 1 minus iota by h cross times vector a dot momentum operator p, this whole times the wave function psi as a function of position vector r. So basically what we have done over here is that we have expanded the exponential function and we have only retained the first two terms in that expansion. And in this manner, from this equation we see that the operator p may be regarded as the generator of infinitesimal translations. Thus, we can obtain the operator for translations, and the operator for translations is given by operator u as a function of position vector a is equal to exponential to the power minus iota by h cross position vector a dot momentum operator. And using this operator for transformations, we see that the wave function psi transforms as wave function psi prime as a function of position vector r is equal to wave function psi as a function of position vector r minus position vector a, and this can be represented by the operator for translations as wave function psi prime as a function of position vector r is equal to operator u as a function of position vector a times wave function psi as a function of position vector r. And using this relation, one can also check that a position dependent operator, operator a as a function of position vector r, is transformed as operator a prime is equal to operator u, operator a, operator u inverse, a result that we have studied earlier also. It is thus easy to verify that the operator u as a function of position vector a, that is the operator for translation, is a unitary operator, and so the norm of the wave function is always conserved. Conservation of linear momentum. Now, taking our discussion for the conservation of linear momentum further, let us see how we can get this result from translational invariance. A physical system is said to be invariant under translations if the Hamiltonian does not change under such a translation. That means if we have the Hamiltonian operator h, which undergoes a transformation to the operator h prime under such a translation, then we can define the new Hamiltonian operator h prime as a function of position vector r as operator h as a function of position vector r minus position vector a, and which turns out to be equal to operator h as a function of position vector r. That means that the Hamiltonian operator remains invariant under such a translation. Now, since the Hamiltonian operator h is a unitary operator, hence we can show that the translation operator acting on the Hamiltonian operator yields the Hamiltonian operator only, that is, the translation operator u as a function of position vector a, the Hamiltonian operator h as a function of position vector r, and the translation operator u inverse as a function of position vector a is equal to the Hamiltonian operator h as a function of position vector r, or the Hamiltonian operator h as a function of position vector r, the translation operator u as a function of position vector r as a function of position vector a is equal to the translation operator u as a function of position vector a, the Hamiltonian operator h as a function of position vector r. In other words, what this means is that the commutator of the Hamiltonian operator h as a function of position vector r and the translation operator u as a function of position vector a is equal to 0, or they both commute, which shows that the unitary operator of translational vectors commutes with the Hamiltonian. Hence, the momentum operator p commutes with the Hamiltonian operator h. That is, the commutator of the Hamiltonian operator h with the momentum operator p is equal to 0. And since we know that if the Hamiltonian operator commutes with any physical observable, then that physical observable is conserved. So in the present case, from this we can deduce that since the commutator of the Hamiltonian and the momentum operator turns out to be 0, hence the linear momentum of the system is conserved, a consequence of the translational invariance of the Hamiltonian. Many particle system. Now, up till now, we were continuing this discussion of translational invariance and the corresponding conservation of a physical observable for a single particle system. Now, let us generalize this result to a system of many particles. So, instead of having a wave function for a single particle, we will now have to write the wave function for n particles. So, the wave function for n particles is given by psi prime as a function of position vector r1, position vector r2 and so on, and position vector rn, where the position vectors r1, r2 and so on, position vector rn are the position vectors of the first, second and so on and the nth particle respectively. And this again from the equations that we have derived earlier, we can see that this wave function psi prime as a function of position vector r1, position vector r2 and so on and position vector rn is equal to exponential to the power minus iota by h cross times position vector a times within brackets momentum operator p1 plus momentum operator p2 plus so on plus momentum operator pn. This whole times the wave function psi as a function of position vector r1, position vector r2 and so on and position vector rn. And further working out this result, we get that the wave function psi prime as a function of position vector r1, position vector r2 and so on and position vector rn turns out to be equal to exponential times minus iota by h cross position vector a dot momentum operator p, capital P, whole times wave function psi as a function of position vector r1 plus position vector r2 plus so on plus position vector rn, where the momentum operator capital P is the total momentum operator and is defined as momentum operator capital P is equal to summation over I going from 1 to n, momentum operator Pi. Now, if the Hamiltonian of the system is invariant under translations, then from the result that we had derived earlier for a single particle system, we can say that the commutator of the total momentum operator capital P and the Hamiltonian H is equal to 0. And from this result, we can then deduce that the total momentum of the system of particles is a constant of motion, or n particle system also, the total momentum remains conserved under translational geometrical translation or invariance of the Hamiltonian under geometrical translation. Translational invariance in time. Up till now, we were discussing translational invariance in space, and we saw that if the Hamiltonian is invariant under such a translation in space, then the linear momentum is conserved. Now, let us see that if there is a displacement in time and the corresponding Hamiltonian remains invariant under such a displacement in time, then what is the conservation law that we obtain? So, what we see is displacement in time leads to the law of conservation of energy. So again, starting in a similar fashion like we did for the spatial translation, we do a translation in time of the wave function psi as a function of r, position vector r, and time t, describing a particle. The wave function translated in time, which may be defined by simply allowing the particle to have its new time coordinate, that is, that the time coordinate now translates from time t to time t prime, where t prime is equal to t plus tau and is the same as the original wave function at time t. That means wave function psi prime as a function of position vector r and time t prime is equal to wave function psi prime as a function of position vector r and time t plus tau. And this turns out to be equal to wave function psi as a function of position vector r and time t. Thus, the translated wave function at time t is then obtained by moving both the time coordinates t and t prime by tau to get the wave function psi prime as a function of position vector r and time t is equal to wave function psi as a function of position vector r and time t minus tau. By expanding this wave function in Taylor's series using the operator del by del t, that is partial derivative with respect to time, and expressing this operator as minus iota by h cross whole times the Hamiltonian operator, we can then get the following results. Energy conservation and invariance in time. Now, based on the definition of the wave functions defined under the time transformation or translation, we get the value or the relation for the translated wave function as psi prime as a function of position vector r and time t is equal to exponential to the power iota times tau times Hamiltonian operator upon h cross whole times the wave function psi as a function of position vector r and time t. This continuous transformation is unitary. That means we can define a unitary transformation operator as u tau is equal to exponential to the power iota times tau times Hamiltonian operator h upon h cross. It means that the events corresponding to time t in the wave function psi correspond to the time t plus tau in the wave function psi prime. Using the transformation operator in time defined above, the invariance of the Hamiltonian under translations in time requires that the Hamiltonian operator h prime as a function of time t is equal to the Hamiltonian operator h as a function of time t minus tau, and this turns out to be equal to the Hamiltonian operator h as a function of time. That is, using the transformation operator u tau, we can write operator u tau Hamiltonian operator h operator u inverse tau is equal to the Hamiltonian operator h, or the operator h, that is the Hamiltonian operator, commutes with the transformation operator u if the Hamiltonian operator h is independent of time. From the above equation, it follows that the total energy of the system is conserved if the system is invariant under translations in time. So students, now let us summarize what all we have learnt in this module. So we started with the definition of symmetry of a physical law, and then we came to know of different types of symmetries in quantum mechanics. From there, we moved on to learn a few familiar examples of geometrical continuous symmetries, such as translations in space and time, their connections with homogeneity of space and time, and to be able to distinguish these from the dynamical symmetries. We also showed the invariance of the Hamiltonian of a physical system under space translations, and we saw that this invariance of the Hamiltonian under space translations leads to the conservation of linear momentum of the system. Similarly, we also showed and learned that the total energy of the system is conserved if the Hamiltonian is invariant under translations in time. Thank you.